Now I would like to talk about an experimental setup that can be used to measure the Maxwell velocity distribution or Maxwell speed distribution. Let's consider a gas that is in equilibrium inside a container. So I have a gas at equilibrium inside this container, and the container has a small hole on the right wall. You can see this small hole has a diameter d. There is a small hole, diameter d is on the right wall. And I'm going to assume that very few molecules will escape through this hole so that the equilibrium is not disturbed. So D must be small enough that very few molecules escape, and the end result is that the thermal equilibrium not disturbed. Okay, so by analyzing the beam of molecules that emerge from this hole, we can determine the Maxwell velocity distribution. So we can use a collimating slit to have a better beam of molecules in which we can analyze the velocity distribution, and the direction of motion of this collimated beam I'm calling z. So let's assume that these molecules are moving in the positive z direction. And by doing this type of analysis, this is going to allow us to determine what kind of molecules are present in this gas. So there's the investigation of atoms and molecules in this beam that is possible. So if I call V bar the mean speed of a molecule, then I can say that if a molecule is close enough to this hole, it's going to spend an average time of the order d divided by v bar in the vicinity of the hole. So near the hole, the average time spent by a molecule will be the diameter d divided by v bar. So you can think of a region with diameter d around the hole, in the vicinity of the hole, and the mean speed is v bar. So the average time it spends, a molecule spends there, is d divided by v bar. On the other hand, I have L, the mean free path, that is the average distance a molecule travels before hitting another molecule. So it's the distance between successive collisions. So this tells us that the average time between successive collisions is basically the mean free path, the average distance traveled in between collisions, divided by v bar. So I would like to have a little or no collisions in the vicinity of the hole, so that basically the molecular velocity distribution is not disturbed. So when a molecule travels through this hole, since it does not collide with any other molecules, there is no redistribution of energy in the system, so the equilibrium will not be disturbed. So if the time required to pass the hole is d divided by v bar, that is much less than the average time between successive collisions, then you can see that the diameter of the hole must be much less than L, the mean free path, the average distance between successive collisions. And this is going to guarantee for us equilibrium is not going to be disturbed. So in the other limit, when d is much greater than the mean free path, we will have many collisions. So I can talk about these two cases. One, if I have the diameter of the hole much less than the mean free path, the escape of the molecules through the hole is called effusion. And in the case of effusion, I have equilibrium not being disturbed, and that also implies that I do not have collisions in the vicinity of the hole. On the other hand, if d is much greater than the mean free path, many collisions will occur near the hole, and then this corresponds to a different type of flow of molecules, hydrodynamic flow. So what I'm interested in here is effusion. So the diameter of the hole should be small enough that the equilibrium is not disturbed, because there aren't any collisions on average in the vicinity of the hole. Only very few molecules will escape through the hole. Okay, so if I want to calculate how many molecules per area per unit time pass through this hole, that's called the particle flux. So I would like to calculate the flux of molecules, the flux of molecules. So I'm going to do this formally using considering the velocity distribution. On the other hand, we had a simple argument about this in the first chapter, or in the beginning of this course. I will revisit that later. So let's say that I have a molecule with a speed v approaching an area with approaching my hole, which has diameter d, and the corresponding area of the hole is dA. So I have the area dA here, and this is making an angle theta with respect to the z-axis. So this is theta, and z, remember, is the direction in which positive z is the direction in which I'm considering the molecular beam to propagate. So this is the speed of a molecule v, and it has time dt to approach and hit this hole. So basically the volume that is contained by this region is here. So let's call this volume dV. So dV, the volume that the molecule will traverse, is going to be equal to its speed v dt multiplied by cosine theta multiplied by dA. So I'm calculating the volume of this region. So you can think of this as a circular cross section here. So basically I'm trying to calculate the volume of this tilted cylindrical region. That is v dt cosine theta. That's going to be the height here. So this will correspond to the height h, which is v dt cosine theta. So area multiplied by the height gives me the volume, v dt cosine theta times dA. Now I ask myself, how many molecules do I have in this region with a velocity v? So I know from Maxwell velocity distribution, f of v d cube v is the mean number of molecules with velocities in the range v to v plus dv per volume. So if I multiply this with the volume, I will get the mean number of molecules with velocities in the range v to v plus dv approaching this hole to traverse through the hole. So I multiply f of v d cube v with the volume dv, so that I will get f of v d cube v v dt cosine theta dA. So this is the mean number of molecules v in the range v to v plus dv. It's not per volume. I have multiplied it with the volume of the region. And now I would like to know the flux, the particle flux or molecular flux. So I'm going to call this f of v d cube v. This is basically going to be the mean number of molecules per area per unit time. So that will be f of v d cube v v cosine theta, because I have divided, this is now per area per unit time. So I'm only interested in the velocities in which I have the vz component greater than 0. So I would like to calculate the flux of molecules that have a speed v to v plus dv, and the speed has to be positive. So this is going to be an integral over all possible velocity components vx and vy. So this is going to be f of v, and then in spherical coordinates for d cube v here I'm going to consider, so this r basically corresponds to my v, and the volume element is basically going to be v square sine theta d theta d phi dv in this case. So it's the volume element of a sphere considering all possible directions for the velocity. So here I will have v square sine theta d theta d phi dv multiplied by v cosine theta. So this is going to give me, if I divide this by 1 over 4 pi n and substitute here e to the minus 1 over 2 beta mv square, 4 pi v square sine theta cosine theta dt d theta d phi and then multiplied by v here. So I'm going to have this multiplied by v dv as well. So, and then I would need to have an n here because I have divided the top and bottom with 4 pi n. So you can see here this is basically going to be integrated over all possible angles that will guarantee that Vz is going to be positive. So I'm going to get for the total flux, so this is not going to be, basically I'm trying to get the total flux of molecules that have a positive speed and that have a positive z component of their velocity. So this is for Vz positive, and that means I would need to consider positive z components. This will be this region in this sphere, so it's going to be this hemispherical part. That means you can see here theta must go from 0 to pi over 2, phi must go from 0 to 2 pi, so that I will be considering only the upper hemisphere, so only z positive z components, so that I'm talking about the molecules approaching the hole. So this is going to be an integral 1 over 4 pi 1 over n integrated over phi equals 0 to 2 pi, theta equals 0 to pi over 2, and here I have the Maxwell speed distribution f of v v dv multiplied by sine theta cosine theta d theta and d phi. Now you can see that this integral and then I'm considering all possible speeds here. So v is going to be going from 0 to infinity, so that's the dv integral. So let me take this dv outside. This is going to be giving me, for the integral of sine theta cosine theta d theta from 0 to pi over 2, this part gives me integral u du, where u goes from where u is sine theta 0 to 1. So this integral gives me u squared over 2 from 0 to 1, which is 1 over 2. The integral from 0 to 2 pi of d phi gives me a factor 2 pi. So the end result for this integral will be the particle flux for this distribution 1 over 4 pi 1 over n, integrate over all possible speeds. V goes from 0 to infinity. I will be considering f of v dv, and then from these two integrals I have a factor of pi. So this part 1 over n f of v dv is the probability of having a speed v in the range v to v plus dv. So this is probability. So probability multiplied by the speed integrated over all possible values then gives me this integral 0 to infinity 1 over n f of v, that's the probability, v dv is going to give me the mean speed of these molecules v bar. These pi's will cancel, so I will get for the total flux of molecules 1 over 4, and remember I had this factor n here. I multiplied top and bottom with n, so I have a factor n here as well. So this is going to give me with this factor n here 1 over 4 n v bar. So this is basically the total flux of molecules that is escaping through the hole. So that is mean number of molecules per area per time escaping the hole. This is called particle flux. If I didn't integrate this over all possible speeds, if I just performed the theta and phi integrals, then I would have for this one the mean number of molecules per area per time with speeds v to v plus dv escaping the hole. So this would be just equal to 1 over 4. I used capital letter F for Maxwell speed distribution, so let me correct this. This is capital letter F for Maxwell speed distribution. So this would be equal to 1 over 4 f of v dv multiplied by d. So that would be without integrating over all possible speeds. Then I would have only considered the mean number of them escaping through the hole in this speed range. Okay, so this f of v dv then would be proportional to v square e to the minus 1 over 2 beta mv square from the Maxwell speed distribution multiplied by v, or it would be proportional to v cubed times e to the minus 1 over 2 beta mv squared. Now this can be experimentally measured using a molecular beam apparatus such as Phys's tooth wheel arrangement. So Phys tooth wheel. So let's say that I have a beam of molecules that is coming from this source. So this is the collimated beam that is going through this apparatus, and I have tooth wheels that are that consists of a disc with one cut that are aligned on the same axis, and these discs will be rotating at an angular speed omega. So if the distance traveled between two tooth wheels here, let me call this distance delta x, the beam travels between these two. So if a beam of particles goes through one tooth wheel, for them to be passing through the second one, you need to have an integer multiple of periods for this, because we need to have completed one full revolution or integer multiple of full revolutions for the beam to go through the second hole. So the distance traveled delta x will be equal to v times delta t, and we have the angular speed omega is 2 pi divided by the period. So delta t has to be an integer multiple of periods. Delta t has to be an integer multiple m times the period, so that it's going to make it m is an integer through the second one. So you would have omega is equal to for the period I would have a delta t divided by m, so 2 pi m over delta t, and since delta t is delta x over v, you would have omega equals to two pi m v divided by delta x. So you can see that omega is proportional to v. So by adjusting omega, I can select the velocities or velocity components in the beam, which will be detected by this detector here. So I can determine what percentage of the molecules will have a certain velocity. So this is the Phys's tooth wheel arrangement molecular beam apparatus. Now if I look at the pressure of the gas inside this container, mean pressure times the volume is nkt, the number of molecules times thermal energy, or mean pressure is number per volume n kt, number density times kt. So the number density or number of molecules per volume is p bar divided by kt. This is for an ideal gas. And at the same time, the average speed of the molecules, remember we have calculated using Maxwell speed distribution. We have found that the most probable speed is square root 2 kt over m. The average speed is square root 8 kt over m. So we have the average speed proportional to square root kt over m. So it's a number multiplied by square root kt over m. So you would have, for the total flux of the particles, uh, 1 over 4 nv bar will be basically p bar over kt, proportional to p bar over kt n, and for v bar I would have square root kt over m. So you can see that the flux depends on the mass. So average pressure divided by square root mt. So the flux of particles depends on the mass of these molecules. Therefore, this can be, so this type of apparatus can be used to separate isotopes with different masses, because the flux depends on the mass. For example, this can be used for separation of uranium-235 separation from a uranium beam. This is called uranium enrichment, which can be used for nuclear fission. That's one technique of separating isotopes with different masses from a molecular beam. So let's summarize what we said. We have a gas inside a container which has a small diameter d. D is much less than the mean free path, so that there are very few molecules escaping through the hole and the equilibrium is not disturbed. And this type of flow is called effusion. If the molecules do go through many collisions near the hole and the diameter is much greater than the mean free path, then it's called hydrodynamic flow. So we're interested in effusion here. I wanted to calculate the total flux of molecules, the number of molecules per area per time passing through the hole. So if a molecule approaches with a speed v in a time interval dt, it's going to be inside a cylindrical air volume that is v dt cosine theta times dA, where theta is the angle the beam is making, or the molecule is making, with respect to the z-axis or positive z direction. F of v d cube v, the Maxwell velocity distribution function, gives us mean number of molecules with velocities in the range v to v plus dv per volume. So if I multiply this with the volume, v dt cosine theta dA, I get the mean number of molecules with velocities in the range v to v plus dv that are going through this hole. And if it is per area and per time, if I divide this by dt and dA, then I have the mean number of molecules with this velocity range, or that will be traversing through this hole. Now I would like to calculate the total flux of molecules. So if I consider for d cube v all possible directions, then basically I can have theta and phi angles, polar azimuthal angle and a polar angle, phi and theta. And in order for the molecules to go through the hole, they must have a positive z component of their velocity, which means that theta will go from 0 to pi over 2. So this is going to be pi over 2 here, from 0 to pi over 2, and phi has to go from 0 to 2 pi, so that I will be spanning the full volume of the upper hemisphere. So that is my d cube v. So and then I have v cosine theta for the volume calculation. So for the total flux here, theta goes from 0 to pi over 2, phi goes from 0 to 2 pi. If I integrate over this, these two angles, then I will be only considering the particles approaching the upper hemisphere with a speed v. So in that case, if I also integrate this for all speed values from 0 to infinity, I will be calculating total number of molecules, total mean number of molecules that will hit per area per time, that will hit the hole per area per time. So for f of v d cube v, I have v squared sine theta d phi dv. That is the volume element for spherical for spherical coordinates, and then I multiply this by v dv, and then I have multiplied the top and bottom with 4 pi n. So by performing the theta integral and phi integral, I have obtained a factor of 1 over 2 and 2 pi here. So 1 over 4 pi n for 4 pi v square e to the minus 1 half beta mv square is the Maxwell speed distribution, v dv times n. So this is basically 1 over n f of v dv is my probability distribution for speed, because f of v dv is mean number of molecules per volume. If you divide it by the number of molecules per volume, it's going to normalize to 1. So that's the probability of having a speed v to v plus dv. So this is probability p of v dv, probability density function. So 1 over n f of v v dv gives me, when I integrate it over all possible values, the mean speed of a molecule. So I have 1 over 4 n v bar for the particle flux, total mean number of molecules per area per time escaping this hole. So if I didn't perform this integral over v, then I would have the mean number of molecules per area per time with speeds in the range v to v plus dv escaping the hole. So I can find out the Maxwell velocity distribution because the flux of the molecules depends on the mass of the atoms and molecules. I can determine from the Maxwell velocity distribution what types of masses are present inside this molecular beam, or I can separate them. So one way is to use this molecular beam apparatus, Phys's tooth wheel. So if a beam passes through one of the wheels, for it to pass through the second one, the time it spans between these two should be an integer multiple of the periods. So t is here the period for one revolution. So angular speed omega is 2 pi divided by the period. The distance they have to travel is their speed v multiplied by dt, delta t. So delta t has to be an integer multiple of the periods. So for the period I have here delta x divided by m. So if you substitute your mt, delta x divided by mv. So delta x divided by mv is the period. So 2 pi divided by the period is omega 2 pi mv divided by delta x, which shows me that angular speed is proportional to v. So by adjusting the angular speed omega, I can determine which molecules I will let pass, and they will be detected and counted by this detector so that I can find the velocity distribution. So I can change this omega and find the different velocity components and count the number of particles that have this velocity using the detector. Okay, so for an ideal gas, I have the ideal gas law, which tells me the number per volume, p bar divided by kt, and the mean speed is proportional to square root kt over m from Maxwell speed distribution, so that the total flux 1 over 4 nv bar gives me a dependence on p bar m and t as p bar divided by square root mt. So at a given pressure and absolute temperature, the flux is proportional to 1 over square root m. So this can be used to separate isotopes with different masses. For example, for uranium enrichment in nuclear fission,